In mid-February 1943, near Sidi Bouzid, Tunisia, amidst the vast, endless sands, a captured American M4A1 Sherman tank stood motionless. A hastily applied German cross barely concealed the still visible American star. Around this prize, officers from the 501st Heavy Tank Battalion gathered, notebooks in hand, ready for analysis. This single American tank, captured intact during the Battle of Sidi Bouzid, sparked a profound crisis of confidence among German engineers, an echo of which haunted their tank development until the end of the war. The fundamental principles of armored warfare were about to be re-evaluated, not because of superior firepower or armor thickness, but due to an aspect to which the Germans traditionally paid less attention: impeccable reliability and operational readiness that simply refused to fail. The tank bore the name War Daddy 2, and its serial number was USA 32641. Manufactured by Lima Locomotive Works, it belonged to Company G of the 1st Tank Regiment, 1st Armored Division. German reconnaissance units undertook an impressive 350-kilometer road march with this Sherman across the North African wilderness to the port of Sfax, a journey that took them 4.5 days. With every kilometer covered, the American combat vehicle demonstrated aspects that contradicted the Germans' established perceptions of the United States' industrial might. The power plant never failed due to overheating. The transmission functioned flawlessly, requiring no attention. The final drives consistently delivered high performance. German tank crews, accustomed to regular breakdowns and forced stops even during minor marches, watched with growing alarm as this enemy machine relentlessly continued its movement across rough terrain that would have quickly disabled their own tanks. At the port, War Daddy 2 was loaded onto a transport ship bound for Germany. The Army High Command issued an emphatic order. This tank was to be delivered to the Kummersdorf proving ground in perfect condition and operational. German intelligence had only fragmented information about the American tank industry, but seeing a real example of the technology made the dry statistical data feel more tangible than ever before. The Sherman embodied mass production on a scale unattainable for Germany, and it was built using automotive engineering principles that German engineers had never mastered. As the ship cut through the Mediterranean waves, heading north, Wehrmacht engineers toiled over preparations for a series of tests designed to shed light on a harsh truth they increasingly recognized: the limits of their own capabilities and the formidable potential of American technology. In the spring of 1943, at the Kummersdorf Proving Ground, located in Germany's picturesque Brandenburg region, the eagerly awaited War Daddy 2 was unloaded from a railway platform. It was assigned the code designation Zugfahrts 259 and the German license plate WH058941. In advance, test engineers had meticulously stenciled markings indicating armor thickness and angles across the tank's surface, meticulously preparing for a comprehensive evaluation program. The Kummersdorf Army Proving Ground, situated 25 kilometers south of Berlin, served as the primary testing ground for both German and captured Allied equipment. Here, meticulous engineers, with German precision, measured, tested, and analyzed every aspect, from track tension to transmission efficiency, recording their observations in detailed technical reports. The Sherman was about to undergo perhaps the most thorough automotive examination that German engineering could offer. The initial inspection was conducted by teams of specialists from various technical departments. They photographed every component and detail from different angles, measured every gap with precision instruments, and scrupulously documented assembly methods that struck them as remarkably simple compared to the complex and sophisticated German approaches. The tank's transmission immediately became a focal point for the experts. While German tanks used spur gears, known for requiring strict tolerances and regular maintenance, the Sherman was equipped with helical gears, which distributed the load evenly across multiple teeth simultaneously. This design principle, standard in the American automotive industry since the 1930s, ensured exceptional durability with minimal manufacturing precision requirements. German engineers considered the production of helical gears an insurmountable challenge for mass production, given their industrial resources and workforce skill levels. Meanwhile, American industry was producing them by the thousands. Tests commenced with a series of standard automotive trials designed to thoroughly scrutinize every mechanical system under controlled conditions. Engineers subjected War Daddy 2 to obstacle courses simulating real combat environments, meticulously measuring fuel consumption, monitoring engine temperature, and recording transmission behavior under various loads and terrain types. After each test, components were carefully disassembled for detailed analysis of wear patterns, identifying signs of overstress, insufficient lubrication, or design flaws. The data obtained contradicted all notions of German tank doctrine regarding the inevitable compromises between performance and reliability. The Sherman, as practice showed, performed quite commendably across all key parameters, and in one aspect even surpassed German tanks, where it was a weak point, namely operational endurance, meaning the ability to operate for extended periods without complex technical maintenance. A detailed study of the Sherman's power plant revealed fundamental differences in design approaches, which explains much about the philosophies of American and German engineering schools. The American tank's transmission had 5 forward gears and 1 reverse, with synchronizers on gears 2 through 5, allowing the driver to shift smoothly without the need for complex double clutching techniques under normal conditions. This made the Sherman almost as easy to drive as an ordinary passenger car, significantly reducing the time and simplifying the process of driver training. German tank crews, in contrast, had to spend considerable time mastering complex double clutching techniques and precise throttle control to avoid transmission failures. The Sherman's designers assumed that these vehicles would be operated by ordinary soldiers with only basic driving skills, while German engineers seemed to rely on highly skilled specialists. At the heart of the American Sherman tank, known as War Daddy 2, was the Continental R975 radial engine, which proved to be an exceptionally reliable unit under a wide variety of conditions. Engineering studies recorded that this engine demonstrated enviable operational stability even at temperatures that would have led to overheating and significant power loss for German engines. The cooling system, despite its simple design, showed impressive efficiency, and the air filtration system successfully coped with desert sandstorms, avoiding frequent clogging, which caused considerable trouble for German tanks operating in North Africa. Every detail of the design reflected the core principle of American engineers, prioritizing practical reliability and functionality over theoretical refinements and optimization. In early June 1943, specifically on the 6th and 7th, a large-scale armaments conference was held at the Hilles Lane artillery range. Reich Minister Albert Speer himself attended the event to assess the current state of affairs. Leading representatives of the German defense industry, as well as high-ranking Wehrmacht officers, participated in the conference. As part of the demonstration program, comparative hill climb tests were conducted, involving both German tanks and captured Allied equipment. War Daddy 2 was displayed alongside the latest German developments, such as the Panther OSF. D, fresh off the assembly line, and the Ferdinand tank destroyer, representing the pinnacle of German armored vehicle engineering. Albert Speer, as the man responsible for Germany's arms production and personally accountable to Hitler for the results, needed to see firsthand what American industry was capable of and assess how well German developments matched the enemy's technology. The demonstration tests revealed aspects that remained uncomfortable for Speer and German tank designers. The American Sherman effortlessly ascended the test slope. Its mechanical transmission, equipped with 5 synchronized forward gears, ensured smooth shifting. The powerful engine maintained stable traction throughout the climb. The Sherman's ease of operation became its distinguishing feature, as demonstrated by the driver. The German Panther, equipped with a more powerful 700 horsepower Maybach HL230 engine, managed to replicate the Sherman's result, but with noticeable strain. The super-heavy Ferdinand, weighing 65 tons and featuring a complex electric transmission, stalled halfway up the incline. Albert Speer witnessed evacuation teams attempting to restart the stalled vehicle. This embarrassment occurred in front of high-ranking officers and industry representatives. In his memoirs, written many years later, Speer recalled what he saw during an inspection tour in Italy in October 1944. He noted the Sherman's superior off-road capability, which easily traversed mountainous areas considered impassable for German equipment. According to Speer, this was due to the Sherman's high power-to-weight ratio, which gave it a significant advantage on rugged terrain. The 26th Panzer Division, in particular, highlighted this advantage. The observations of Germany's Minister of Armaments carried significant weight in the highest circles of the Wehrmacht. The influential German weekly Das Reich published an article on June 27, 1943, providing a public assessment of the Sherman tank. The article presented the Sherman as an outstanding achievement of American engineering, a highly commendable product of North American steel industry. Particular emphasis was placed on serial production and the American industry's ability to satisfy almost arrogant demands. Journalists noted that the gyro-stabilized gun was the first attempt of its kind ever made anywhere, acknowledging the innovation of American engineers. Despite the propagandistic nature of these statements, designed to conceal signs of defeat, anxiety grew within German engineering circles. It became clear that American tanks were not merely meeting requirements, but were surpassing German counterparts in their operational characteristics. Meanwhile, at the Kummersdorf Proving Ground, German engineers conducted comprehensive tests of the Sherman throughout the summer and autumn of 1943. They meticulously measured the tank's operational range, subjecting it to extended endurance tests. The results showed that the Sherman could cover over 2,000 km before requiring major overhaul, which was 4 times the capability of early Panther models in real combat conditions. Furthermore, the transmission's high efficiency, surpassing all German counterparts with minimal power loss, was noted. The synchronized mechanical transmission provided smooth and easy gear changes, eliminating the need for complex techniques such as double clutching and precise rev matching, which were required on German tanks. The final drives were another revelation that forced German engineers to reconsider their tank design concepts. The Panther tank, developed in Germany, inherited a flawed final drive design from its predecessor, the Tiger, which became the Achilles heel of this combat vehicle. Engineers used spur gears in housings that proved insufficiently robust for a 45-ton tank. Wehrmacht mechanics fighting in North Africa and on the Eastern Front constantly reported breakdowns that often forced Panthers to be abandoned after short marches, sometimes not exceeding even 100 kilometers. At the same time, the Sherman, an American tank, used helical gears, similar to those employed in its transmission, which ensured high reliability. The Sherman's final drives rarely failed, even in the harshest combat conditions that quickly disabled their German counterparts. Decades later, during restoration work, Shermans were found whose final drives required no repair after years of storage. This attested to a significant structural resilience that surpassed all expectations. By the end of 1943, Kummersdorf, the German testing center, had accumulated enough data to compile detailed reports that were distributed among Wehrmacht technical units. These documents, intended for high-ranking officers and officials of the Armaments Ministry, presented a sobering comparison of capabilities. The Sherman represented the maturity of the American automotive industry, which Germany, despite all its theoretical knowledge and scientific expertise, had failed to achieve. The approach to tank production in the US and Germany differed significantly, ultimately affecting their combat effectiveness. American industry, relying on mass production methods, allowed for certain deviations from the ideal that might have seemed unacceptable in German precision engineering. However, this approach led to the creation of more reliable machines, capable of functioning better in harsh field conditions. A crucial factor was parts interchangeability. Thanks to this, repairs to American tanks could be carried out in the field using a basic set of tools and minimal specialized training. While German machines required factory precision and specialized equipment for many types of repairs, the American design philosophy prioritized keeping machines operational. The focus was not on achieving theoretical performance maximums that looked impressive in specifications, but on ensuring reliability and maintainability in combat conditions. German engineers, analyzing the situation, noted that American industrial advantages extended far beyond simple production metrics. American automotive manufacturing had decades of civilian industry development behind it, which Germany could not boast on a comparable scale. In the pre-war years in the US, car ownership was commonplace for citizens of all economic classes. In Germany, however, automobiles remained a luxury item, accessible only to the wealthy and the party elite. The Volkswagen program, promised to German workers since 1934, had delivered fewer than 1,000 civilian vehicles by 1939. This vast difference in the maturity of the automotive industry was also reflected in tank design philosophy. While American engineering created tanks that could be serviced by mechanics with basic skills acquired in civilian auto repair shops, the The German approach involved developing machines that required highly skilled personnel with years of military technical training. By late 1943 and early 1944, as field reports accumulated, the comparison of German tank reliability became impossible to ignore. Panther tanks, in particular, required strict adherence to operational limitations to avoid mechanical breakdowns that could disable them. Drivers were instructed to avoid frequent gear changes, as this led to transmission damage. The third gear proved so vulnerable that field manuals strongly recommended using it only in emergencies. Furthermore, Panthers could not turn while moving in reverse due to the risk of transmission failure. Pivoting in place was only possible if the ground resistance was identical on both tracks, which significantly limited their tactical maneuverability. Foreign objects in the running gear could jam the drive sprocket, requiring hours of maintenance to rectify the malfunction. Notably, all these problems arose despite Panthers being produced in specialized tank factories by skilled workers, using the best materials available to Germany. In contrast to German tanks, the Sherman was the product of automotive engineers from General Motors, Ford, and Chrysler. They transferred mass production principles, honed over decades of creating civilian automobiles, to tank manufacturing. The tank's design made maximum use of commercial automotive components, relying on existing supply chains and manufacturing expertise. Transmissions were supplied by various manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company, with all parts manufactured to uniform standards and being fully interchangeable. This standardization, characteristic of the American automotive industry, remained an unattainable dream for German tank manufacturing, where each manufacturer introduced minor variations that prevented true parts interchangeability. Throughout 1943 and 1944, new captured Shermans arrived at Kummersdorf, seized from British units in Italy and Soviet forces on the Eastern Front. Each captured vehicle underwent thorough testing, allowing for the creation of an extensive database on American tank capabilities in various variants and production periods. Of particular interest to German engineers were Shermans re-equipped by the British with 17-pounder anti-tank guns known as Fireflies. This variant, which addressed the Sherman's main deficiency in firepower, demonstrated the growth potential inherent in the original design. German engineers noted that the Sherman's large turret ring allowed for the installation of a significantly larger gun with minimal modifications. The Panther, hastily put into production to counter Soviet T-34 tanks, lacked the ability for significant armament upgrades without a complete redesign of the turret and the vehicle. The testing program for American M4 Sherman tanks underwent significant modernization, incorporating reliability tests designed to recreate the harsh realities of combat. Engineers subjected the Shermans to grueling trials, driving them hundreds of miles over rugged terrain, meticulously recording every mechanical failure, maintenance requirement, and component breakdown. The collected data was then compared with reports from units operating German Panther and Tiger tanks on the Eastern and Italian fronts. This comparative analysis revealed a clear superiority in reliability for the American vehicles. For most of 1943, the combat readiness of Panther tanks averaged no more than 40%, with some units reporting critically low figures, reaching 20-25%. Certain Panther battalions recorded periods where fewer than 1 in 5 tanks were capable of performing combat missions. Concurrently, Sherman tanks demonstrated significantly higher operational readiness across all theaters of war. German field reports meticulously documented the Panther's reliability issues. During Operation Citadel at Kursk in July 1943, the Panther's operational readiness was a mere 16%, with mechanical breakdowns disabling more vehicles than enemy fire. By December 1943, the readiness figure had only risen to 37%. Reports for February 1944 recorded 37% combat readiness, reaching 50% by April 1944. It was only in May 1944 that 78% was achieved. These figures represented the percentage of Panthers capable of combat missions on any given day, while the rest were inoperative, awaiting spare parts, or undergoing repairs. Gradual progress in improving reliability was observed as design flaws were addressed. Yet even the best Panther readiness figures never matched the level initially achieved by Shermans from the start of their production. By late 1943, even for the most unbiased analysts scrutinizing the facts, the superiority of American engineering became evident. The diesel engines of Sherman tanks, with proper maintenance, demonstrated a service life exceeding 3,000 kilometers. In contrast, Panther engines, despite all efforts to modernize and correct initial flaws, barely lasted 1,000 kilometers. German reports from March 1944 proudly announced that Panther engines had achieved a lifespan of 1,000 kilometers, presenting this as significant progress. However, even after these improvements, Panthers could boast only 1/3 of the reliability of diesel Shermans. Sherman transmissions were robust and required minimal maintenance before overhaul, and synchronized gears reduced the likelihood of breakdowns due to driver error. Panther transmissions, conversely, demanded constant monitoring and frequent repairs. Failures of the third gear were so common that drivers had to master the technique of shifting directly from second to fourth gear to avoid using the problematic ratio. Sherman final drives displayed enviable reliability in conditions that regularly led to the failure of Panther final drives after just 100-200 kilometers of operation. German field reports from units employing captured Shermans in battle served as compelling confirmation of the conclusions drawn at the Kummersdorf proving ground, demonstrating their alignment with the realities of war. German mechanized units, suffering from an acute shortage of reliable equipment due to the deteriorating condition of their own tank fleet, readily adopted any serviceable American tanks that fell into their hands. Notably, unlike Soviet T-34s, which underwent extensive modifications before use, Shermans entered Wehrmacht service in their original form. The absence of a need for any modifications was due to these vehicles functioning flawlessly, lacking design flaws that required immediate correction. German tank crews, exhausted by the constant breakdowns of their own machines, were astonished by the Sherman's reliability, a fact they frequently mentioned in their letters and reports. Tank regiment reports emphasized that Sherman crews could fully concentrate on tactical maneuvers and improving combat effectiveness, while their counterparts in Panthers and Tigers were constantly forced to worry about whether they would even reach the battlefield without breaking down or complete their assigned mission before technical malfunction incapacitated them. In January 1945, during Operation Nordwind, the 10th SS Panzer Division captured a dozen American M4A3 Sherman tanks in the vicinity of Hellesheim. These vehicles, belonging to the US Army's 43rd Tank Battalion, fell into enemy hands in full working order after their crews were forced to abandon them during the rapid German advance. Subsequently, these captured Shermans were integrated into the 13th Company of the 10th SS Panzer Regiment, where they were actively used in combat until the very end of the war. The German command employed these tanks as reconnaissance vehicles and mobile reserves, roles requiring a high degree of reliability and the ability to travel long distances without frequent maintenance. This choice reflected the recognition that American tanks, as demonstrated by the Kummersdorf trials, were highly reliable and dependable. This quality, rather than just firepower or armor protection, became the decisive factor in their tactical value during the final months of the war. Amidst severe resource shortages and the deteriorating technical condition of German equipment, a Sherman capable of arriving on the battlefield with a working gun was far more valuable than even a more powerfully armed Panther that might break down 20 kilometers from the front line. In January 1944, as Wehrmacht forces were retreating on several fronts, the testing programs at Kummersdorf were significantly expanded to include captured equipment. Engineers meticulously studied the American M4A1 tank, equipped with a Continental R975 radial engine, carefully documenting its technical parameters and conducting comparative analyses with other variants. Particular attention was paid to the M4A2, powered by a twin General Motors 6046 diesel engine. Its outstanding fuel economy and other unique operational characteristics were noted. Furthermore, the M4A3 with a Ford GAA V8 gasoline engine, which American tankers rightly considered the most successful Sherman powertrain option, underwent a comprehensive evaluation. Despite differences in engines, all variants exhibited a common trait: exceptional reliability of the running gear. This was due to both well-conceived engineering solutions and high-quality manufacturing processes. The stability of characteristics across various modifications deeply impressed German engineers, who were accustomed to significant fluctuations in the quality of products from different factories, even for formerly identical machines. Regarding the vehicles, the M4A2 diesel tank particularly impressed German engineers studying the equipment at Kummersdorf. Soviet forces received 4,102 of these vehicles via Lend-Lease, and a considerable number fell into German hands during retreats on the Eastern Front. The twin GM6246 diesel engine provided the Sherman with a performance comparable to any other variant, while consuming significantly less fuel than its gasoline counterparts. This was a critically important advantage given Germany's dwindling fuel supplies. German designers also experimented with diesel tank engines, but abandoned these developments due to manufacturing complexities and fuel injection system issues. American industry, by contrast, produced diesel Shermans concurrently with gasoline versions without disrupting production schedules. This demonstrated production flexibility and technological sophistication that German industry was unable to achieve under wartime conditions. In March 1944, General Inspector of Panzer Troops Heinz Guderian noted in his official reports that by early 1944 the Panther's reliability had reached, in his words, acceptable standards. Engine life had been extended to 701,000 kilometers, and main drive problems were largely resolved through design changes and improved manufacturing processes. German military reports pompously announced improvements in production processes. Yet this achievement only allowed the Panther tank to reach a level of reliability that the American Sherman had possessed since its initial production in 1942. Germany's war machine celebrated reaching standards that American designers had surpassed long ago, vividly demonstrating the deep lag in German armored vehicle industry. The comparison became increasingly dismal as German tank production desperately struggled with intensifying resource shortages and devastating Allied strategic bombing. Allied air campaigns with increasing precision and power struck key links in the production chain for Panther and Tiger tanks. The Maybach engine plant in Friedrichshafen suffered a crushing blow from RAF Bomber Command on the night of April 28, 1944. This raid involved 322 aircraft and is recorded in the Imperial War Museum archives as the most destructive attack on German tank production during the entire war. The attack also destroyed the CF gearbox plant located adjacent to the engine factory. As a result, the production of tank engines and transmissions was completely paralyzed for a full 6 months. The resumption of German tank production in November 1944 was marked by a sharp decline in quality standards. Forced labor, which became commonplace in German tank factories due to the conscription of German workers into the army, led to acts of sabotage by the laborers. Cigarette filters were deliberately placed in oil channels. Gaskets were installed incorrectly, and components were assembled without adhering to necessary tolerances. Sherman production avoided such problems thanks to the location of American factories far from the combat zone and the presence of motivated workers who received decent wages in good conditions. The key difference between American and German tank production lay not so much in engineering knowledge as in industrial capacity and fundamental design principles. German engineers possessed a deep understanding of automotive principles and extensive theoretical knowledge on par with their American counterparts. However, they failed to consistently apply these principles to tank design, prioritizing other factors. German tank designers, striving to create vehicles with outstanding tactical and technical characteristics, often sacrificed reliability in real combat conditions. The pursuit of impressive figures at the expense of practicality became the Achilles heel of German armored vehicles. For example, the Panther tank, armed with a powerful 75mm Kammerbüke 42 gun and protected by thick frontal armor, suffered from an overloaded powertrain that struggled to cope with the vehicle's 45-ton weight. In turn, the formidable Tiger required complex maintenance and frequent repairs, making it dependent on highly skilled specialists. Such compromises might have been justified if German industry had possessed sufficient production capacity to produce the necessary quantity of tanks and spare parts. However, under escalating Allied bombing and acute raw material shortages, this task proved insurmountable. In contrast to the German approach, American engineers, with years of experience in mass automotive production, designed tanks that could be produced in tens of thousands and maintained by mechanics with basic training, utilizing skills acquired in civilian life. Simplicity and reliability became key factors, ensuring American armored vehicles' numerical superiority and effective deployment in a wide variety of conditions. The Sherman tank's design prioritized practicality and reliability, unlike German tanks. The Sherman's powertrain utilized components well proven in civilian technology, and design principles were borrowed from the automotive industry. The electrical system included a backup generator, capable of traversing the turret even with the engine off. This feature, which seemed superfluous to German designers, proved indispensable in combat conditions. German tankers could only envy such conveniences, especially when the turret traverse mechanism failed with a stalled engine on a slope. These features were not included in German technical requirements because German designers prioritized armor thickness and firepower. By the spring of 1944, Wehrmacht units on all fronts reported an increasing number of mechanical problems related to deteriorating production quality and a shortage of spare parts. Panther tanks required rail transport for movements exceeding 100 kilometers, as their final drives could not withstand long road marches. The German command faced a serious problem. Field commanders issued strict directives limiting the movement of Panther tanks. This was done to preserve these combat vehicles for actual battles, rather than losing them to technical malfunctions during marches. Paradoxically, the Berge Panther recovery vehicle, built on the Panther chassis to evacuate broken-down tanks, suffered from the same reliability issues as the tank it was designed to save. The situation on the front became increasingly dismal. Breakdowns disabled more tanks than enemy fire. In some units, up to 70% of tank losses were due to technical malfunctions, not combat damage. At the same time, American industry continued to ramp up Sherman tank production at unprecedented rates, unattainable by Germany. During the war, American factories produced 49,324 Shermans, exceeding the total production of all types of German tanks. Sherman tanks were supplied in vast quantities to Allied forces via Lend-Lease. British Commonwealth forces received thousands of these vehicles, and the Soviet Union received over 4,000 diesel variants. Chinese forces in Burma effectively used Shermans against Japanese armor, which was significantly inferior in performance to both American and German designs. Every theater of war where Sherman tanks served graphically confirmed the results of the Kummersdorf trials. With proper maintenance, these vehicles demonstrated astonishing durability, continuing to function reliably in extreme conditions that proved fatal for German armored vehicles. German tankers who managed to capture Shermans and use them for their own purposes consistently noted their outstanding mobility in numerous letters, reports, and post-war interviews. Reports from the Eastern Front emphasized that even the complex multi-bank Chrysler A57 engine, composed of 5 separate cylinder banks, seemed simpler for German mechanics to maintain than the temperamental German tank engines, which required specialized knowledge and equipment. Highly valued by Allied crews for its exceptional reliability and power, the Ford GIA V8 engine astonished German mechanics who were accustomed to Maybach engines that required constant adjustment of valve clearances, ignition timing, and carburation. Even the twin General Motors diesel engine, rejected by the American Army as less reliable compared to gasoline counterparts and sent via Lend-Lease, significantly surpassed any diesel engine that German industry could produce for its tanks in terms of operational characteristics and reliability. An undeniable advantage of the Sherman was its significant design margin, which was eventually highly appreciated by German specialists. Initially designed for a 30-ton M4 with a 400 horsepower engine, key components of the transmission and final drive required no significant changes to handle the 42-ton M483 jumbo assault tank which featured reinforced armor. These same components, which powered the standard Sherman, effortlessly transmitted 650 horsepower from experimental engines without requiring reinforcement or modification. German engineers typically viewed such excess in design as an inefficient use of resources, believing that superfluous capacity led to increased production costs and consumption of scarce materials without immediate visible benefit. American designers, in contrast, understood that a safety margin allowed for future upgrades and enhanced vehicle reliability in combat conditions, justifying the additional costs over the machine's entire life cycle. By the summer of 1944, when Allied forces landed in Normandy, German tankers realized that their armored vehicles' technical problems extended far beyond the shortcomings of individual tanks. The dominance of American artillery, powerful air support, and immense logistical capabilities collectively overwhelmed German forces, regardless of their tanks' characteristics or commanders' tactical prowess. The reliability of Shermans allowed American armored units to conduct continuous combat operations, which was unattainable for German panzer divisions. American tank battalions could launch attacks, sustain battles, pursue the enemy, and immediately prepare for new operations without spending time on prolonged maintenance. German panzer divisions were forced to conserve their few operational vehicles, understanding that every movement brought them closer to a mechanical breakdown. It was this difference in operational readiness that determined which side could exert constant offensive pressure and which had to carefully conserve its limited combat resources. Recognition of superiority. The use of captured Shermans by German forces in battles became an undeniable testament to the triumph of American automotive engineering in the eyes of the Germans. This fact spoke for itself, confirming the reliability and effectiveness of American equipment in the harshest conditions. The 150th Panzer Brigade, created with the specific purpose of conducting diversionary operations during the Ardennes offensive in December 1944, sought to acquire captured American tanks for camouflage. German strategists specifically preferred Shermans, having heard of their legendary reliability and low maintenance. They understood that in a complex and risky operation, where every detail mattered, a Sherman could be a decisive factor for success. Despite all efforts, the brigade only managed to obtain 2 Sherman tanks, and only one of them was in a combat-ready condition. Unfortunately, this single operational Sherman never saw action due to colossal road congestion, which thwarted the brigade's plans to penetrate enemy lines. In an operation demanding flawless equipment, performance far from supply lines and any support, only American equipment offered a realistic chance of success. German tanks, even in ideal condition, could not guarantee the stable operation required for such missions. This episode vividly confirmed that in certain situations, the reliability and ruggedness of equipment play a decisive role, surpassing even firepower and armor. January 23, 1945, marked the official collapse of the German automotive industry. The Tank Commission submitted a report meticulously detailing systematic final drive failures across all types of German tanks. The report's conclusion offered a merciless assessment of the situation. On the eve of the 1945 Eastern Offensive, the German tank fleet was severely crippled, 500 piece. These 370 Panthers and approximately 100 Tigers were sidelined due to faulty final drives. To this grim list were added another 200 Hetzer self-propelled guns, built on the Czech 38-ton chassis. Lieutenant General Wolfgang Thomele, Chief of Staff to Guderian's Inspector General of Armored Troops, offered a harsh evaluation of the operational consequences. Under such conditions, any systematic deployment of tanks was out of the question. Soldiers lost faith in the reliability of their equipment and, in critical situations, abandoned perfectly functional vehicles due to final drive problems, fearing they would get stuck and become easy prey for the enemy. German tanks, designed to inspire awe with their advanced technical specifications, failed to meet the most crucial requirement for armored vehicles: sufficient mechanical reliability to reach the battlefield and accomplish their assigned missions. In early 1945, as Soviet forces relentlessly advanced on Berlin, the Kummersdorf testing center hastily prepared for evacuation. Engineers frantically gathered test data and dispatched documentation to facilities further west, hoping to preserve technical information for post-war analysis. Some of the captured tanks, including at least 2 Shermans, were urgently integrated into improvised combat units, desperately defending the approaches to Berlin. These machines fought shoulder to shoulder with German tanks in the final fierce battles, providing a last real-world comparison. The Shermans continued to operate until they were destroyed by enemy fire or abandoned due to lack of fuel. German tanks, including Panthers and the few remaining Tigers, broke down due to mechanical failures with astonishing frequency, shocking even experienced crews accustomed to their low reliability. The story of War Daddy II and the many other Sherman tanks tested at the Kummersdorf proving ground stands as a prime example of an industrial paradox during World War II. German engineers, working within a system that prioritized theoretical perfection over practical suitability, created tanks that appeared formidable on paper but proved unreliable in sustained combat. Meanwhile, American engineers, drawing on their extensive experience in automotive manufacturing, developed tanks that, while perhaps less technically sophisticated than their German counterparts, demonstrated high reliability and dependability in the harshest conditions where German equipment failed. In armored warfare, as in most military operations, a weapon capable of functioning flawlessly when needed is preferable to one that may be theoretically more advanced but unable to reach the battlefield and perform its assigned task. Post-war analysis by American and British intelligence organizations confirmed the conclusions reached by German testers at Kummersdorf. A thorough examination of knocked-out German tanks revealed that mechanical failures were as frequent a cause of their loss as direct combat damage. Final drives failed under overload, transmissions jammed due to insufficient lubrication or crew error, and engines burned out from overheating or lack of oil. Germany's fascination with creating individual pieces of equipment with outstanding characteristics proved to be a costly misstep, obscuring the decisive role of reliability and ease of maintenance. Engineers designed tanks that required highly qualified specialists, not ordinary conscript mechanics, to operate. The engines of these machines needed constant oversight from experienced technicians, and the logistical system couldn't handle the burden of supplying numerous units with unique parts. The experience gained at Kummersdorf directly influenced German tank designers in post-war West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, priority was given to reliability and maintainability rather than maximum tactical and technical performance. Developers carefully studied American approaches to automotive engineering and deliberately applied them to military equipment. As a result, the Leopard 1 inherited many design solutions that ensured the Sherman's success: a robust powertrain with ample power reserves, ease of maintenance requiring minimal special tools, standardized components for rapid field repairs, and the ability to upgrade without radical changes to the design. In the annals of the Cold War, the Leopard 1 holds a special place as one of the most successful tank designs. Its construction proved so in demand that it served with many countries and was produced for decades. The captured Shermans discovered at Kummersdorf, including the famous War Daddy II, with its inscription preserved on its armor, were not merely examples of enemy equipment to be studied. They embodied the triumph of mature industry and proven engineering solutions based on real combat experience. These qualities proved more important than theoretical innovations detached from manufacturing realities. German engineers, in developing their tanks, gambled on advanced characteristics, believing that technological superiority could compensate for a lack of resources and numerical enemy superiority. However, as practice showed, they were mistaken. In contrast, American tank builders, drawing on the harsh experience of war, created reliable and easy-to-maintain machines. They understood that in modern mechanized warfare, logistics, maintainability, and constant combat readiness are crucial for victory. This approach proved correct and played a key role in the outcome of many battles. The reliability gap between the American Sherman and German tanks had a profound impact not only on tactical armored warfare, but also laid the groundwork for a broader understanding of the critical importance of military-industrial capacity in modern conflicts. Germany entered World War II with advanced technical solutions across various weapon systems, relying on scientific knowledge and engineering developments that surpassed the capabilities of most of its adversaries. However, Germany lacked the developed industry and production capacity needed to sustain this superiority through large-scale and continuous manufacturing, especially while fighting on multiple fronts simultaneously. In contrast, the United States entered the war, perhaps with less technically sophisticated weaponry initially, but possessed an enormous industrial potential that allowed it to produce weapons in colossal quantities, continuously improving quality, reliability, and operational characteristics based on real combat experience. This industrial approach, exemplified by the design and production of the Sherman tank, proved significantly more effective than the German reliance on technical complexity realized in small-batch production. During World War II, the economic power of the United States became a decisive factor in determining the Allied victory. American industry demonstrated unprecedented productivity, manufacturing weaponry on a scale unimaginable for Germany and other nations. The US managed to produce almost as many Sherman tanks as the entire German industry produced tanks of all types. Moreover, the American economy not only supplied its own armed forces, but also provided vast quantities of equipment and materials to allies through the Lend-Lease program, all while maintaining a high standard of living for its population. Such economic achievements, which remained unattainable for Germany even before the start of massive strategic bombing, determined the outcome of the war with the same inevitability as the bloodiest battles on the fronts. The mathematics of war was simple and ruthless. A Sherman tank with a 75mm gun, which reliably reached the battlefield and effectively performed its tasks, was far more valuable than a German Panther with a superior gun that frequently broke down on the way to the front or required lengthy maintenance after each day of combat. A tank battalion with 80% of its vehicles combat-ready could successfully accomplish missions that were utterly beyond the capabilities of a battalion where only 40% of tanks remained operational. Equipment reliability was not just a matter of convenience or a secondary factor. It was the foundation of operational effectiveness, determining whether armored units could carry out their assigned tasks and make a decisive contribution to achieving victory. Throughout World War II, German tanks systematically failed this crucial test, while American machines demonstrated consistent reliability. By mid-1943, tests conducted at Kummersdorf had irrefutably confirmed this fact. Despite this, the German command continued to insist on the use of Panther and Tiger tanks, whose impressive firepower and armor could not compensate for their low reliability in critical situations. The Sherman tank won World War II not through superiority in firepower or armor, but through industrial supremacy, which manifested in its mechanical reliability, constant availability, and ease of maintenance. German engineers at Kummersdorf, based on comprehensive test results, recognized this by mid-1943. They compiled detailed reports, meticulously documenting their findings and repeatedly verifying the evidence with scientific precision. As a result, they arrived at correct conclusions regarding the advantages of American equipment. However, as is well known, recognizing a problem and solving it are entirely different challenges. In the context of a brutal multi-front war, where enemy resources significantly surpassed German capabilities, Germany's industry proved incapable of rapidly reorienting production towards reliability. At the same time, American industry, hardened by decades of competition in the civilian sector, successfully integrated principles of reliability into automotive manufacturing and effortlessly extended them to military production, achieving outstanding results. The War Daddy II tank, the sole Sherman captured in Tunisia and subjected to thorough analysis at Kummersdorf, became a vivid example of the mechanical reliability and stable operation of American equipment. Every kilometer it traveled without breakdown testified to the strategic era of German tank design, which prioritized characteristics over reliability. Every test demonstrating the superiority of the American automotive industry confirmed that practical experience and mature production were more important than theoretical calculations. The comparison of the Sherman's reliability with that of German tanks convincingly proved that Americans had successfully solved problems that German engineers didn't even recognize. The Sherman itself was one of 49,000 mass-produced units, yet its significance for German self-perception was immense. It became a symbol of Germany's defeat in the industrial war even before the fighting concluded. The Sherman clearly demonstrated that American manufacturing power surpassed German technical sophistication and tactical skill.